So today we will discuss about the recursive language, recursive enumerable language, decidable language, partial decidable language, and undecidable language. In case of recursive language, the Turing machines will always halt. In case of recursively enumerable language, the Turing machines will halt and sometimes may not halt sometimes. So during the decidable language, which is a recursive language, where the Turing machines will always halt, and in case of partially decidable language, where it is a recursively enumerable language, where the Turing machines will halt sometimes and may not halt sometimes, and where whenever the undecidable language, there are no Turing machines for that language. So now I give an example for we have a problems. So first of all, we need to know that is the problem is solvable or unsolvable problems. So the problem is solved by the any kind of computers or digital computers or general purpose computer or any kind of machines. So first of all, we need to know that is a problem decidable problem or undecidable problem. So if the problem is decidable, so it can any Turing machines will always halt for this problem. So we have a such kind of algorithm and we know the procedure. So the algorithm will get some output after finite times. But in case of undecidable problems, we don't know the time to solve these problems, but that we know the procedure to solve this problem. So this is the basic difference between the decidable problems and undecidable problem, but both are solvable by the any general purpose computers or any Turing machines. So now the word is the time and space complexity of a Turing machines. So in case of Turing machines, there are maximum number of moves which will the Turing machines shall make to accept or reject a string of length n in the worst case scenario. And in the space complexity, maximum number of cells which Turing machines shall make use on Turing tape to accept and reject for string of length of n in the worst case scenario. So the time complexity is like that, the maximum number of moves, and the space complexity is like that, that is the maximum number of cells which Turing machines shall make to use on Turing tape to accept or reject or string of n number of length n in a worst case scenario. So that is time and space complexity for Turing machines. So now the comes to the point, that is the charge and Turing thesis. So that is the way you have to know that is a problem can be solved by any algorithm if and only if it can be solved by a Turing machine. So that is very important. That is a problem can be solved by any algorithm if and only if it can be solved by any Turing machines. And another way that anything that can be solved by any current digital computer can also done by a Turing machines. And currently there are no problem which can be solved by a digital computer cannot be solved by any Turing machines. And many mathematical models are suggested, but not on all, not one of them is more powerful than the Turing machine. So the charts Turing thesis. So any problem that can be solved by any algorithm, so if and only if it can be solved by any Turing machines. So now I need to know what is the halting problem. So given a problem, okay, so will it is halt? So that's why given a Turing machines, will it halt when run or some particular given input string. So now the given some programs written in some programming language, will it ever get into an infinite loop or will it always terminate? So that is the halting problems. You have already known about the Turing machine. So Turing machines have such kind of output, so it can accept and halt, or it will reject and halt, and it will name it will loop. So suppose the halting problem is like this: the given a Turing machines, will it halt when it run on some particular given input string. So in a general, we can't always know, and we have to write any programs, and we have to use some programming language, and we have to solve these programs using any general purpose computer. So the best we can do in run the programs and see whenever it halt, so it will get some output. For many program, we can see that it will always halt or sometimes loop. So whenever it is sometime loops, so it will go infinite times. So it will not get any output from these programs. So now, what is the reduction technique? So we say that A is a problem and A is reducible to a problem B if a solution to a problem B can be used to solve a problem A. So suppose A is a problem and it is undecidable, so it will not solve it. It is not it solved. So now this problem is reducible to a certain problem B, and this problem will be solved by solved. So that's why this problem B will be solved. So the A will be also solved. If I given an example, if A is a problem of finding some root of x to the power 4 minus 3x squared plus 2 equal to 0, and B is a problem of finding some root of x squared minus 2 equal to 0, and then A is reducible to B. So as x squared minus 2 is a factor of x to the power 4 minus 3x squared plus 2, a root of x squared minus 2 equal to 0 is always a root of x to the power 4 minus 3x squared plus 2 equal to 0. So first of all, a problem which is reducible to a certain problem B, and if a solution to a problem B can be used to solve the problem A, just like an example. So now the reduction technique is, if A is reducible to B and B is decidable, then A is decidable. So A is reduced to B, so A reducible to B, and B is decidable. So B, the problem B will be halt for certain input. So A will also be halt for certain input. And the same thing, that if A is reducible to B and the B is undecidable, then A is also undecidable. So now we have to discuss about the universal Turing machines. The name is the Turing machines, but the universal Turing machines, that's like a UTM. So the language ATM, A sub TM, is equal to M, that is the Turing machines which will accept W. So M is Turing machines and M accept W. And the T is the Turing machines recognizable. So what does it mean? So the given the description of the Turing machines of some input, and can we determine whether the machines accept it, and we have to simulate or run the Turing machines on that input. And if you get some answer that M accept W, of our algorithm will hold and accept, and M reject W, so our algorithm will halt and reject, and M loops on W, so our algorithm will not halt. So that's why, so the universal Turing machines for an input, M, the description of some Turing machines, and W is the input string for M. And action, we have to simulate the M and behave just like a M would may accept, reject, or loop. And the universal Turing machine is a recognizer, is not a decider, because sometimes in case of your general purpose computers, when you have to write any programs to run in these general purpose computers, so that the general purpose computer acts like universal Turing machines, and your programs in some programming languages is like a Turing machine. So the input M, just like your programs, and the W, which is by input we have to given to your M, your Turing machines. So it will simulate M. So you have to run your programs, and whether your programs will give you some output, and it will accept and reject, or it will go infinite time. So it will loop. So it is not a decider. It is not a decider, because it will not accept, reject, but it will have a loop. So it will something, the universal Turing machine is a recognizer, so such that, so the A sub Tm, where the M comma W, where the M is a Turing machines and M accept, W. So that's all. If you have any query, you can mail me or you can contact my phone number. Thank you.